Alright, hell yeah. So we have the hardest problem in physics, and this is the first problem in this book, which is crazy. This is chapter 1. So it says that these atoms reside in the corners of cubes. The thing that messes you up is this red line. You know what I mean? You almost need to research how atoms are stacked in cubes, and so if you make this cube and you'd be like, okay, the atoms are at the corners, then this distance is 0.2 nanometers. Okay, cool, now what? In the video I talk about how if this doesn't cleave at 45s and you just pull them apart, well, the distance between them is just the distance 0.2 nanometers. But when we're cleaving them at 45s, they pack tighter. And we see this with this representation. I would draw a side view, and then you can see that, hey, look at the center of these two atoms. They're much closer than the actual width of an atom. That's the width of an atom. This distance is a little bit less. And because they pack in, they overlap, you know what I mean, center to center, because they're off. You know, I think you can see that. So that's what they're talking about with atomic planes. In the long part of this video, we definitely explore how it's very representative of how, like, hey, this ruler has 1/16, and that's okay, but check this out, 1/32 is more accurate. So you're getting a more accurate, because there's more layers packed in, and so your atomic planes are closer together. And so they want to know the distance between atomic planes, and that's that distance between those representative layers. Well, let's just call it that. So I come over here to my drawing, and we know this is 0.2, this is 0.2, and then we draw an arrow there. So that's what we do right here. And then this is D. This is that distance between atomic planes. So now this problem requires you to use geometry. Pythagorean's theorem when it comes to triangles, and we have 0.2 and 0.2 nanometers. I would write in Pythagorean's theorem, a squared plus b squared is equal to c squared. So we can find c by saying c is the square root of a squared plus b squared. Cool. And then, but we really want to find this distance d, so we can also, you know, I mean, this is 8th grade, but I would always write Pythagorean's theorem, and then I would always write that, hey, a triangle is 180 degrees. And if you have a right triangle, cool, then it's going to be 90 plus 45. This one has to be 45. Cool. So then when we split it up again, this is our right triangle. This is 45. This must be 45. Therefore, these two distances must be the same. So this distance right here is just half of this distance c that we're finding. So our equation for d is just half of c. C is the square root of a squared plus b squared. And then I decided to get tricky. Instead of 0.2 nanometers, let's just turn this into 2/10 of a nanometer. Cool, because then we can kind of use some fractions, and we can say that this distance d is going to be 1/2 of c, so we got 1/2 of the square root of 2/10 squared plus 2/10 squared, and so this is going to be 4 100ths. You know what I mean? 4 100ths plus 4 100ths is 8 100ths. Cool, and we still need to take the square root of it and divide it by a half. But we can factor out, you can always say this is the same thing as square root of 8, square root of 100. We know what that is. So cool, we got 1/20th times the square root of 8. Now you can say, you need to factor out that, so we have 8 is 2 times 2 times 2. And then you can always do this. You can always take the square root of the individual ones. We can see that square root of 2 times square root of 2 is just 2. So we're going to have 2 divided by 20 times square root of 2. Well, obviously 2 divided by 20 factors to 1/10, and we're going to have 1/10 square root of 2, or basically just square root of 2 divided by 10. I mean, or you could just throw it in your friggin' calculator and get 0.141, but basically we have the square root of 2, which is 1.414, but we're dividing by 10, so we get 1/10, you know what I mean, kind of that. Alright, so that's the distance, and that distance is smaller, you know what I mean, because our the 0.2 nanometers is how far the atoms are stacked, you know, kind of this way. But if we stack them at 45s, they hook together a little bit tighter because they overlap. So if you made a ruler out of kind of a 45 degree, you know what I mean, as those atoms are, you would get a better ruler. That's what I explained in the long video. So hell yeah, that was pretty good for about 5 or 6 minutes. So thanks for joining me on that one. That's the fast version. And now, man, this is the first video that I've made since coming back from my road trip. And man, we're just working out the kinks. But thanks for joining me. You know, my goal is to do the first chapter of this physics book because people kind of want some easier problems, and so do I. So hell yeah. So if you want to stick around for me just trying to bash through this one to get my game back, go for it. Alright, thanks for joining me, and hell yeah. Alright, hell yeah. So we have Physics for Scientists and Engineers, and this is volume 1. And so this is problem 1, so first chapter. And so my plan is to kind of do all the first chapter problems. So, and we'll see how far we get. You know what I mean? And I was on a big vacation, kind of a road trip, so I apologize, you know, if some of the content's not that good. But I just need to get back into the swing of things. Now, this is one of the most difficult first chapter, you know what I mean, problems. And it's number 1. So the first thing that you have is this, and it makes no sense. So the thing to pay attention to, I think, the most is disregard this outlined red box. There's another gentleman who makes the video, and the person uses the red box to actually kind of go through the center of the molecules. So we're going to talk about that. I think you could do something like this. You could draw a larger box. You know what I mean? Because if we're saying this is an actual molecule, you wouldn't be able to see it anyway. So you would have to scale it down. So I think, you know, even just doing this, and then we'll, you know what I mean, do that and that. And then so even just doing this and saying, hey, look at this little box right there. You know what I mean? And you could do that. So this little box, hey, maybe that is this. Where we can take, so we're just saying, hey, this is some sort of like crystal or rock. So it's a crystal inside. It's like a quartz crystal, or who cares, you know what I mean? But it's some sort of rock or glass rock, you know what I mean, crystal. And we're going to take a little chunk of it that's down to the molecules. Now, when we do it, you know, these red lines indicate that, hey, the whole thing kind of looks smooth, you know, on all sides. It's a whatever, it's not a square, it's whatever the other thing's called. It's like a rectangular cylinder. I have no idea. But anyway, so the tricky thing about this, well, it asks, I don't even know what it asks. You know, it basically says when you pull this thing apart, when it breaks, they're asking, hey, what is the distance, this distance, between the two cleaved surfaces? You know what I mean? So that gets kind of confusing. So let's not do it at a diagonal. Let's pretend this thing doesn't cleave at a diagonal. That's going to make this problem easier. You know what I mean? So that could be the first thing that you do is we're just going to say when it breaks, these molecules are just like that. So when you actually do break it apart, there you go. You got 3 in a row, 3 in a row. And then so the distance between these molecules, if that makes sense to you, you know, I mean, who cares anyway? But that distance is just going to be kind of the dimension of one of those molecules. So it's center to center. And so if those molecules are touching, if two circles are touching. Now this, I like this problem because it gets into geometry. And geometry is king when we're talking about physical materials. I don't know, just like geometry and dimensions. Like where things are located, like whether they're circular in shape, whether they're rectangular in shape, whether they're like, you know, triangle in shape, you know what I mean? Alright, so if this thing cleaved, you know, like this, the question would be, well, what's the... And what is the question? It says, calculate the spacing d between two adjacent atomic planes. I don't even know atomic planes, and I think that is very bizarre wording in itself. Yeah, this whole thing is just really difficult to kind of wrap your mind around, because, like, hey, when it cleaves, like, the second it cleaves, there is going to be no gap, like, even, so we're gonna do, kind of how it is. So we're gonna say this thing cleaves right through here, because that's kind of what they're getting at. So it's gonna cleave along this surface. So when, and let's draw this. So we're going to do 1, 2, 3, 1, and then 1, 2, and then 1, 2, 3, 1, 2, and then 1. So when this surface cleaves, well, the second it separates, you know, I mean, there kind of is no gap between, you know, the molecules or whatever. So I think it's just worded very bizarrely. Calculate the spacing d between two adjacent atomic planes. Now, this is the only thing that makes sense to me. Alright, hell yeah. No, this will be good. Because when, so I think we can, this atomic plane thing, I think we can get some geometrical, you know, just like, if we don't know what they're asking, but we can get there. So if we do have, if you have anything, let's say you have a crystal, you know, and then you break it, hey, you know, you have like maybe this going on. Cool. So let's say, and it used to look like this, and you took it and you broke it. Well, guess what? Like this right here is the surface that you can see, touch, feel. And these are atoms. So I think, like what I'm getting at is the take-home point is that you can't break up these molecules. Or, well, let's just say they're individual atoms. Let's say it's like a salt crystal. Well, that's NaCl. Damn it. Alright, hell yeah. No, we're good. I mean, because in the picture it says these are atoms stacked up, and so this is a crystalline solid it's not molecules together. These are just atoms. So there you go. So whatever it is. I don't know my periodic table very well of what could be a solid and what could be packed in this, and then what could cleave at a 45. You could look that up. That would be a very good investigation to figure out what element on the periodic table is a crystalline solid that cleaves at 45-degree angles. Got it. But what I'm getting at is that we can understand this atomic planes from the perspective that if you do cleave, you know, a solid that consists of just singular atoms, then when you do break that, you'll get a plane. You know what I mean? Hey, you got an atom right there. So you could come in and you could remove those three. So this, I guess that took a lot of breath, but that's kind of what I'm getting at, is that you could now separate these two from those three. What you can't do is separate, you know what I mean, let's say a half. You can't do this. You can't, you know what I mean, do half spheres and then over here do half spheres. Sorry I'm writing so small. But this you cannot do. So then it's just kind of cool to be like, oh, okay, so I get that aspect. So we can like remove a row of molecules. Okay, so now here's where I can best explain why this distance, this spacing between the atomic planes when they're 45 is going to be less than. And from geometry we could just see that. And we're going to do that last, you know what I mean? Because the first part of this problem is just to investigate and figure out what the hell is going on. So I simplified it by this, and let's see. So then, if we do have atoms that are, oh darn it, let's see. So let's do a grid. Put these circles in here. Okay, so, and let's do that. Just do one more. Okay, so let's take a look at, so out of 45, what I'm looking at is these 3 atoms, and when I do this, you know what I mean? Hey, these atoms overlap. You know what I mean? So if we had, so let's, thanks for bearing with me. So let's say we did have these 3, and we didn't want them to overlap. You know what I mean? So we actually say, hey, there's an atomic plane, and then when we go stack the next molecules up against it, you know what I mean? Well, to do that, we would either have to stack them like touching right here, and it would basically look like that, just with a bigger gap here. But if we put them right here, well, what would happen is the atoms like wouldn't be you know, connected. You know what I mean? So there is an element of like, hey, atoms, you know, are occupying some sort of, let's say, spherical space, and then that's going to be adjacent to another atom. Now, and this brings up the question is like, well, are you going to have any overlap? You know what I mean? You might. You know what I mean? Because at that point, we're not talking about, because if we're saying this is a full atom, you have all your protons and neutrons inside, and then your electrons on the outside. So, but I think from a physical perspective is that you won't have too much interplay. You know what I mean? Let's say you have like the orbital, so you have protons and neutrons, and then you have like your first orbitals and your second orbital. I don't even know how that works out, but you probably wouldn't have you know, 2 molecules like this where the orbitals will be, you know what I mean? This you probably wouldn't have. Now you probably might have some, if you have electrons in a couple orbitals, you might have some sort of interconnection, you know what I mean? So it's not a 2 perfect spheres, you know, with any sort of overlap or gap, you know what I mean? Yeah, you could probably have a little bit of a gap, a little bit of overlap. And that is just a straight guess. But it's stuff like that that's going to make this problem make more sense. Alright, hell yeah. So now we're going to explore kind of this atomic planes and how we can use a physical representation to, I don't even know what words I'm saying, but, you know, just as an example of how to make sense of this. Because I said you can't chop up atoms in half. So if you're talking about, hey, this column of atoms, it's 1, 2, 3, 4, 5, 6, 7, 8. It's 8 atomic planes, you know, in this direction. And so you could lop off, let's say, that plane, and then you would have 7 atomic planes. And then, so let's say that's your measurement. And so I guess where we're going with this is that if the atomic planes that we're measuring are at a 45-degree angle, and we're going to stack them at a 45-degree angle, we can get more atomic planes for the same length. And so I think let's grab a new sheet of paper. And yeah, let's Alright, what I want to do is kind of do a graphical representation of maybe what's half. So I'm going to draw a circle over here and then say, hey, that's the middle, and then I'm going to come here, cool, and then I'm going to draw that same circle right here, cool, did it, and then I'm going to draw this down here, and then I'm going to come over here and draw another circle, and then I'm going to come over here and draw another circle. Okay, hell yeah. And then I guess I'm going to, I don't know, let's just say these are kind of funky shapes. And so I can actually draw that in, and then do that, and then do another one right here. So what we have, and let's say when we do cleave this, what happens is that these two separate, so I can just draw it fairly fast. And let's say they're still connected somehow, you know what I mean? This would still be a, well, let's see if we can actually make this make sense. So yeah, this, oh, sorry about this. So yeah, these, so we can say that the cleave will be in between these molecules. So you would have this one, this one, this one, and that one when it cleaves, and then you would separate it by this, that, this one, and that one. Alright, so that probably doesn't make a whole lot of sense, but what we're showing, and you know, I really should draw more of them in, because if you drew a lot of them in, you could cleave at any of those points. And that also means if that's how we're cleaving this, then you could also just remove those two. You know what I mean? So if you were just to cleave the last two off, cool, those two are gone, and now our dimension gets this. So if our measurement, if we're taking a measurement and getting some number right here, and then we cleave those two off, well, cool, now we get a new number, and now we can measure that width. And again, these are atoms, so we can't just cut off half of them and then get a number. Holy hell. But what I'm showing here is that if these atoms can kind of overlap where their centers, see how this center and this center is now just a half of an atom away. You know what I mean? Compared to, even if we did it at a horizontal angle, if it looked like this, then we could say that the center of this atom compared to this atom, this is going to be a whole atom away. So that's the distance between those two. And man, and I just apologize, I'm just not like on point on this one. But what I thought was the coolest thing for a representation of this is it's a ruler. So if I use this as my ruler, that's 8, 1, 2, 3, 4, 5, 6, 7, 8. It's essentially, well, let's just say it's this, 1, 2, 3, 4, 5, 6, 7, 8. So that's basically my ruler. It's 1/16. You know, this ruler is chopped in 1/16. But if let's say I have the ruler sideways, and I stack them sideways like this, and I just and then I count the rows this way, you know, I would say I have, and I'm not going one row, 2 row, 3, no, there's multiple rows. So we got 1 row, 2 row, 3 rows, 4 rows. Let's see if I can actually do this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sweet. So even, yeah, I've never done that before. I've done this problem before like this. But now, from here, you know, and you would have to, like, obviously, and this distance might not be the same. Like, obviously, but you know, from here to here, you're going to have 10 layers, and it's going to be probably even a shorter distance than this distance. This distance is going to have 8 atoms, or no, I'm sorry, not atoms, but 8 layers. You know what I mean? You have 8 atomic planes making up this length, but if you stack them horizontally at 45-degree angles, this distance between this atom and that atom, and with atomic planes, you're going to have 10 atomic planes, and then the distance could actually be smaller. It could be a shorter distance than, and I would imagine it is. You know what I mean? And then I made an example where the distance is half. So if we compare this ruler, which is divvied up into 1/16, that would be like this, going this direction. But if we put them at atomic planes going this way, we just made our ruler, in this example, 1/32. So you get a ruler that's just twice as accurate. Anyway, that is like literally the only... I thought it was a pretty good example. Alright, hell yeah. So now let's do this problem, and what I would do is just draw a side view. So I would do this, and I would say 1, 2, 3, you know, and I would just start drawing them in. And what I would... But yeah, it is fascinating that they calculate the spacing between 2 adjacent atomic planes is still kind of fascinating to me. The way that's worded is just really difficult for me to put words to. All right, hell yeah! No, this could be the best verbal explanation. Let's say we're adding an atomic plane. So I have it already cleaved, and we have this, but then over here I have something that looks like this, and it would kind of technically probably have to look like that. You know, it'd have to be kind of 2 atomic planes, but you could, for this, I'm just going to say, hey, like this is a solid. This is 1 atomic plane, and for whatever reason it's holding its shape, and then we're going to insert it right into here. And when we do, we want to know how much extra height we get out of this. So we are going to measure from the normal direction, you know what I mean? So we're going to say, hey, this is where we cleaved. This is our measuring point, and that's where I think making this such a small cylinder, you know what I mean. I would probably do this. I would say, hey, let's take a huge box, and then right here we're going to, you know, we're gonna have a 45-degree angle, you know what I mean, right there that's cleaved off this box. And then so we want to know the distance. You know, that's all I'm getting at. You know, it's just for whatever reason, since this is in a, you know, kind of a tight cylinder, it messes up like where you're measuring from. Because it just always seems like you're going to be measuring along this direction. You know what I mean? Or measuring along, you know, an orthogonal or perpendicular direction. But that's not true. So you really have to say, like, hey, this is an actual chunk that, like, this is the plane that we're working from, and we're going to measure normal to that. And so when we add another atomic plane in, we want to know how much this grows in height. You know what I mean? So that's one verbal way to say, oh, okay, I get it. You know, because when we tuck in those 2, like, or those 3, did I do this right? 1, 2, 3. When I tuck in those 3, this is how much the height grew. And if we drew our picture right, you know what I mean? Hey, this is actually how much the atom is width. So the height only grows. It definitely grows more than 50%. You know what I mean? Of the atom height. So we're talking to maybe like 0.7. You know, 0.7 per, like 70% of the atom height. Okay, hell yeah. So now we have an idea of where we're going from. Now, it does give us, it says the atoms reside at the corners of the cube the atoms reside at the corners of cubes of length 0.200 nanometers. Now, this is another reason why this red line will mess you up doing this problem. Because for this problem, you really want to research how atoms are packed together. And this totally spells it out, but like you probably in chemistry you haven't even like done this before. But, because what it's saying is that, hey, we're taking some sort of cube, and we're saying that the atoms are on the edges of the cube like that. So there you go. If you have a cube, we have 1, 2, 3, 4, 5, 6, 7, and then there's an atom over there. You have 8 atoms. You know what I mean? Because if you look up the organic chemistry tutor, it does a very good job of doing, there's like 3 different ways to organize these. One, you could have, an atom in the middle, and then you would have one tucked there. You know what I mean? You would have 8 all around. So then you would have 9. You know what I mean? So that's another way to pack these. But I don't know. I bet you that one in the middle would have to be a different shape. So yeah. So maybe this is probably wrong. Yeah. So we could see. Yeah, how could you pack atoms? Alright, hell yeah. So I just looked it up, and obviously, these layers are just kind of resting on top, and that's, you would shift them so each of these fit in the pocket, and if you did that, you would get a hexagonal, like it would be like hexagonal orientation. I know with cubes, there's like 3 different types. But anyway, so that's all the information that I care about. And so now we can, let's print out a new sheet of paper, and then, so if this distance from center to center is 0.2 nanometers, which, so a micrometer, that's not a micrometer. I think this is a micrometer. That's 10 to the negative 6 meters. So this is also, anytime you're going past millimeter, you know what I mean? Because like I don't think people, like millimeter, I don't think you associate that with, 10 to the negative 3 meters. I think we know that 1,000 millimeters is 1 meter. So then that means that 1 millimeter is, well, you would have to divide by 1,000 and divide by 1,000. And so this is the same as 1 divided by 10 to the 3, and that's 10 to the negative 3. Sweet. So that's kind of how I did that. And yeah, so and then, yeah, if you get, yeah, if it's, like a micrometer is 10 to the negative 6, nanometer is going to be 10 to the negative 9 meters. Cool. So now we have 0.2 times 10 to the negative 9 meters. I think that's how I would write it. I guess you don't have to. Might as well just write it 0.2 nanometers. And, okay, so now we know that this is 0.2 nanometers. So now it's total geometry. That's where I would take this and do a side view and say, hey, this distance between there and there to there is this 0.2. But what we want is, and then we'll just draw a triangle right here. What we want is this distance. So right there, this leg of that triangle is this distance D. And so how do we find that? Well, we need to, this is where you're going to use Pythagorean's theorem. Yeah, I swear, anytime you're dealing with triangles, definitely just write Pythagorean's theorem. It might seem weird to actually write it, and you can just write it in a bunch of different ways. You could say C is the square root of a squared plus b squared. There you go. Just a bunch of different ways to write it. You could write it in more ways. You could say, hey, b is c squared minus a squared square root of that. So 3 different ways to write it. Because we definitely need to know this distance right there. So let's draw this triangle, even though it's a little bit sloppy. So this is 0.2, this is 0.2. So cool, we can know what this total distance is right here. And then the other thing that we know about, what do we know about this length? Well, we know that this is a right triangle, and we know that this is also, like, this is a 45-degree angle, and if this is 90, then this is also 45. You know what I mean? So if this is, these angles are the same, this distance right there is equal to that distance. Sweet. So when we find this total distance, we can divide by 2 to find that distance is equal to that distance. So there's just a lot of different ways to go about it. I think this problem actually sucks, because you're just like, I can't, you don't even know what the hell's going on up till this point. And then I would say this mentally is just like, man, this Pythagorean theorem sucks. You know what I mean? Because you kind of have to figure out why that, how this side is related to this side. Well, it's because these two angles are the same. So once we find that, so if we already know that this c is the square root of this plus this, this squared plus this squared, and then that's going to be this total thing. We know what this is, just divide by 2. So you can do it all in one go, and you could say you have 1/2 the square root of 0.2 squared plus 0.2 squared. Well, that's going to be 2 times 0.2 squared. You know what I mean? So you could even do that. 0.2 squared. That's going to be 0.2 times 0.2, which is 4, but you got to move that decimal place to 0.04. And then you got to multiply by 2, so we got 0.08. And then you got to take the square root of 0.08 and then multiply by half of that. I don't even know what this is. Break out our calculator, square root of 0.08, and then multiply by 0.5. And so we get a distance of 0.141 nanometers, which isn't the square root of 2. It's like the square root of 2 divided by 10. You know what I mean? So it's the square root of 2 divided by 10. I don't know if that simplifies anymore. And I don't even know if this answer is right. You know what I mean? Hopefully we did something wrong. But final answer, 0.141 nanometers, and I think we beat this to death. What a horrible problem, you know what I mean? The fact that I can come back, I've already done this one a couple years ago, and I can just come back to it and it's still just absolutely heinous. So 0.0141 nanometers. Okay, hell yeah. So, I mean, should I just leave this in just garbage form, or should we do a quick version? I want to do a quick version because I really like, just throwing my time and effort into a problem and showing you, like, hey, I suck at this stuff. I have to look up stuff online. My brain doesn't work. And it probably does. It just feels like your brain doesn't work. And I swear, like, my brain feels not as good as it did 2 months ago. So it's fascinating. You know what I mean? And that's life. You go to college and you're just like, oh, dude, my brain does not work this week, this month, this semester. And then other times it's crispy, and you're just like, whoa, we can just do anything. So that's why I'm going to I'm trying to get back into this, and I don't mean to talk like an idiot, but we'll work on that too, because with a lot of, if I know what, if you can totally tell, if I know what the hell I'm talking about, we'll just talk normal. But else, you know what I mean, we'll try to have a good time. And, yeah, hell yeah. So my plan is to just do some of these easy physics problems. But this one wasn't. This is the worst. And in college, I got this, and it's just, yeah, that sucks to be like, whoa, the first problem that you get for your first year in physics is this, and it makes you not want to do physics ever again. You know, no one says like, oh, you should be looking stuff up, you should be doing more than just what the problem is. No one tells you any of that stuff. But I think we did a good job of explaining atomic planes and how it could be useful because, you know, if you cleave those atomic planes at a horizontal, hey, you're going to get more atomic planes lined up. Instead of just 0.2 nanometers apart having these atomic planes, you can stack them up 0.14. So that distance is a lot narrower. And then, you know, with maybe atomic microscopes, you can actually count, hey, that's how many we have, so that's our measurement for that, maybe. You know, so you get a better ruler. That's the only way I can make this problem make sense. With 45-degree angles, you get a better ruler. So if you have something like this, if you have a crystalline structure where you know how many atoms are packed like this way, but also at 45s, you would always want to measure, you'd always want to use this, you would always want to cut this to where all your planes are at 45s, and that would be a better ruler. So again, the analogy is, hey, this part of the ruler is better than that part of the ruler. Alright, hell yeah. So let's make the short version at the beginning. Thanks for joining me, and that's a video. Alright, hell yeah. So I'm making the quick version, you know what I mean? And as I'm doing this, when we do the Pythagorean theorem, we got 0.2 and 0.2. And it was just so fascinating to me that, hey, what is 0.2? That's 2 divided by 10. So you can write this as a fraction. And now we have 2 divided by 10, and then 2 divided by 10 over here. And then so when we do Pythagorean's theorem, it's 2 divided by 10 squared plus 2 divided by 10 squared. And this is pretty cool because this is going to be 4 divided by 100 plus 4 divided by 100. That's going to be 8 divided by 100. You know what I mean? So that's our answer there, and it's obviously the square root of that. Sorry. So if we're trying to find this distance, the hypotenuse C, we have the square root of 8 divided by 100. And now you can factor this. You know what I mean? You can say 2 times 2 times 2 is 8 divided by 10 times 10. And then so when we do the square root, you know what I mean? This is so cool. We've done this a lot. Is like, hey, this is the same thing as the square root of 2. You know what I mean? Square rooting each number. It's also the same thing as, you know, you can group them together, or you can, you know, you could do this. You could be like square root of 2, like do that. You know what I mean? You can always do that, and you'd be like the square root of 10 times 10. And then so we would have the square root of 4, square root of 2, square root of 100. And that's obviously going to be 2 divided by 10, square root of 2. Sweet. And so there's just a lot of different ways to get there. You know, if I look at it like that, I can't just go right to, I can't say that this is 2 divided by 10 square root of 2. You know what I mean? Okay, so that's C. The problem asks for this distance D, and we're saying, hey, half of C. So C divided by 2 is that distance D. And so if we take 2 divided by 10 square root of 2, if we divide this by 2, you know what I mean? It's the same thing as multiplying by a half. The 2's cancel, and we end up with the square root of 2 divided by 10. That's where square root of 2 is 1.414, you know what I mean? And then divided by 10, well, that's going to be 0.1414 nanometers. That's where we go from. This distance is 0.2 nanometers, and then the atomic planes, the distance between cleaving atomic planes on 45-degree angles is 0.1414 nanometers. Sweet. So that's just going to be, I'm probably not going to do that in my quick version, but we'll see what we do. Hell yeah.